All right, welcome to your first screencast for the chemical reactions unit. This is a big unit. We're going to cover everything from chemical reactions, acids and bases. We're also going to cover equilibrium and equilibrium reactions. So there's a lot going on in this unit. So I'm just going to get started. So chemical reactions, this is just a basic chemical reaction showing you a typical format. Objective number 1, identify different types of chemical equations. There's word, skeletal, balanced, molecular, complete ionic, and net ionic, and basically just what are the different ways that chemical reaction equations can be written. So identifying chemical equations, this is kind of the first thing that we need to do, is make sure that we can identify different chemical equations. In a chemical reaction, new substances are formed. That's the whole point of it. It is a chemical change. You're making something new. Chemical equations are the language of chemical reactions, so we use words or symbols to describe what's happening. That's why it's so much easier to not write it in word format, but write it in the symbols format, and you'll see that as time goes on. So there are different types of ways to write the same chemical equation or the same chemical reaction. The first one would be in words. So you literally just write it out in words. Uses words to describe the reaction. Like lead 2 nitrate and potassium iodide solutions, so that tells you that they're both liquids, react to form solid lead 1 iodide with potassium nitrate solution. So it tells you that the lead 1 iodide is a solid and the potassium nitrate is a liquid. And all you would do is just write it out, write out the chemical symbols for that. The next type of equation is a skeletal equation. The skeletal equation is basically you're writing only the compounds, you're not balancing it. So if I were to look at only the compounds here, I have the same equation from above. I've just wrote out lead 2 nitrate as Pb parenthesis NO3 parenthesis 2 plus Ki, potassium iodide, reacts to form PbI2, which is lead 1 iodide, and then KNO3, which is potassium nitrate. So I'm just writing this out using the chemical equations. Next type of equation is a balanced equation. This is the one that we will work with the most. So identifies and quantifies the amounts. So you put coefficients in front of things. Objective number 3 is all about balancing chemical equations. So this is the same chemical equation as before, except now I've balanced it to make sure that I have the same number of atoms of each element on both sides. So I have 1 lead, 1 lead. I have 2 nitrate groups here, but because there's a 2 in front of this, I have 2 nitrate groups over here. I have 2 potassiums, I have 2 potassiums. I have 2 iodines on this side, I have 2 iodines, so it is balanced. This is the one that we will use the most. The next type is a molecular equation. It contains the states of any of the compounds, so whether they're ionic or molecular. So the same thing above, the same thing as here, except now I've written down what the actual states are. And remember from the previous one that it said that these guys were solutions, which means they're dissolved in water, so they're aqueous. That's what AQ means, aqueous. This one it said was a solid, and this one also said that it was a solution, so it's aqueous, and that's why those symbols are used behind it. The last 2 types are the complete ionic and then the net ionic. A complete ionic equation will show all ions or compounds present during the reaction and their states. So if you look at this one, all I've done is just break them apart. So on this side, instead of having lead nitrate, I just broke it apart. Lead 2 plus into the nitrate with the 1 minus charge. And potassium iodide, broke it apart. I'm still using the same coefficients that were in front of the compounds or the subscripts, like with the nitrate that was with the compound previously. And I have also broke apart the potassium nitrate, this aqueous solution of potassium nitrate. You'll notice that I did not break apart the solid here, and this is where we're going to have to use solubility tables to determine if the solid will break apart or not. The reason I'm not going to do that is because this solid is insoluble, meaning it will form and it will stay a solid and it will stay a precipitate, so it's not going to break apart into its individual ions, so I'm not going to break it apart into its ions. And that's where the last one, the net ionic equation, comes into play. The net ionic equation shows only the ions or compounds involved in the actual reaction, so no spectator ions. And in this case, the ones that are really involved in the reaction, because these guys don't really change that much, NO3 stays NO3, PB stays PB, or potassium stays potassium. They don't really change that much. What you do see is the lead now bonding with the iodine, forming this insoluble solid. So that's my net ionic equation, showing the ones that are really only reacting. These two, the lead and the iodine, are really the only ones reacting, as the other ones just stay dissolved or stay aqueous in the solution. This is what we will deal with in objective number 4. So when we get to objective number 4, we'll be writing ionic equations and net ionic equations. You'll get lots of practice with them. So each way of writing a chemical equation has pros and cons. Different chemical equations are better for different types of reactions, and I'll let you know when we're going to use what type. But like I said previously, the balanced chemical equation is the one that we will use the most. So the summary format for objective number 1 is a 3-2-1 format, and that's all you need to do for this objective.